closed loop integral of E dot dl must be 0 everywhere. And the only way that nature can do that is by making the charge distribution on the surface uniform. And that is amazing when you think of that. It's independent of the position of that charge plus Q inside. So if you start to move around with that charge plus Q inside, the outside world will not know. The outside world only knows that there is a charge plus Q uniformly distributed on the outside, because it is a sphere. That would not be the case if it were a heart. But the outside world has no way of knowing that you are moving that charge inside around. So I'm sitting inside there, and suppose I crawl inside there with a rubber rod and with a cat. And I use the rubber rod on the cat, creating positive and negative charge, same amount. The outside world will not know, because I don't change the charge inside. I only have this plus Q in my pocket. The fact that I create plus on the cat and maybe minus on myself, the outside world will never know, because the sum of the charges is still Q. They may hear the cat scream. That's all they can hear. But they have no way of knowing that I'm fooling around there with charges. And so, the outside world has no way of knowing what happens on the inside. And we call that electrostatic shielding. That's the effect of a Faraday cage. I want to demonstrate, when I bring this can in the electric field, it's a conducting, hollow object. I bring it in an electric field of the Van de Graaff. The thing is a conductor. I will show you that because of the induction, you're going to get, like you see on that figure, you're going to get negative charge on one side, positive charge on the other side, and zero charge on the inside. That's quite amazing, isn't it? If this were positive, let's assume it is, then this side becomes negative, this side becomes positive, the whole thing is in equipotential, no charge inside. Quite amazing. So let's turn on this. The Van de Graaff. So we create that electric field. We turn on the electroscope. Here is my little ping pong ball, conducting. And I'm going to touch first the can on your side, on your left side. There we go. And I bring this charge on the electroscope. Boy, nice charge. I now touch the other side, and I will approach the, I heard a spark. Sparks are always bad. I approach that electroscope, and if the reading of the electroscope, if the deflection becomes less, as we discussed earlier, it means that the polarity that I have on here is different from the polarity on the electroscope. And you clearly see that. The deflection becomes less. So the charge that I took off from this side has a different polarity than the charge that I took on from that side. But yet, it's an equipotential. All that strange polarization of charges takes place at the surface. And now I will try to get inside to see whether I can get some charge from the inside, and there shouldn't be any. Ooh, I have to take this charge off, of course. And I touch this, and you see no charge. So you've seen three things, which is quite amazing. That the charge on this side has a different polarity from the charge on that side, and that everything happens on the surface, nothing happens on the inside. I could not get any charge from the inside. Now, we're going to experiment with more dangerous stuff. And that is with the Van de Graaff. Here you see a Faraday cage which has some openings. It's not solid conductor, but it has small openings, which doesn't change the situation too much, maybe only a little. And I'm going to go inside that cage. This would also be a nice Faraday cage, but it's very hard for me to crawl in there. And if I go in there with a radio, just like the radio in your car, then you may not be able to hear the radio, even though radio waves is a difficult story, because the shielding that we discussed is only electrostatic shielding, and radio waves are electromagnetic radiation, which strongly changing fields. So it may not be as perfect a shielding as you may think. But we all know if someone breaks off the antenna of your car, which happens in Cambridge all the time, you have no reception inside. Because your car is a Faraday cage. And so what I will do, I will go into the cage. I will first show you that when we charge that cage, that we bring it up to a few 100,000 volts. I'll just hold some tinsel in my hand to convince you that, yes, indeed, this cage will be charged by the Van de Graaff, provided there is contact here. And we'll see that, yes, Marcos, give me the full blast. Let's just look at the tinsel. You see this tinsel clearly indicates, like an electroscope, that I'm being charged now. So I'll jump off if you can discharge. Then I will go inside. I will have the tinsel with me. So I will show you that inside there, when they charge that cage, that the tinsels will not spread out. And I will bring with me this wonderful radio. And
a woman who opposes embalming is a suspect.
I didn't plan that, believe me.
Catherine Padilla, grandmother of 10, denies the charges and tells a reporter she's not, quote, an assassin.
I'll first go in without any charge. So don't do anything.
She's 55 and she's formed what she calls her own tradition.
Nothing. I'm shielded. However, there is a problem. You can still hear me. And I'm wearing a transmitter. And the receiver is somewhere outside this box. So why can you still hear me? That means that the kind of radio waves that I am transmitting, a very high frequency, it's not a static field, so somehow they can get through. So the shielding is not perfect for fast-changing electric fields. But it's good enough for AM radios. So now I'll go in, and I'll try to be brave, and he's going to try to zap me now, to electrocute me. But since I've taken 802, I'm not afraid. I've done my head, that's a different story. Okay, Marcos, do the best you can. Here are the tinsels. Running up, 100,000 volts, 200,000 volts. I feel as happy like a clam at high tide inside here. Nothing is happening. I'm not worried at all. If lightning were to strike me, who cares? I'm in a Faraday cage. Not going to spoil my weekend. I can touch the inside. There's no charge anywhere here. My weekend won't be spoiled, and I hope that the new assignment is not going to spoil yours either. See you next Tuesday.